Warning, the video you're about to watch contains mathematics at the level of college algebra and trigonometry. All material has an assumed prerequisite of both Algebra 1, which is elementary algebra, and Algebra 2, which is intermediate algebra. While some prerequisite topics are reviewed briefly, a more thorough review of these entrance topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes.
Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. This video is a continuation of a series of videos on polar coordinates and the polar coordinate system. You should have already watched the video on the polar coordinate system and how it's built, and how to convert ordered pairs from polar coordinates to rectangular coordinates. Now we're going to go the opposite direction, which is converting ordered pairs from rectangular coordinates to polar coordinates. This has a little bit of a caveat in it because, as we mentioned earlier, if you have a point in the rectangular coordinate system, let's say your point's 1, 1, there are actually an infinite number of representations of that point in the polar coordinate system. For example, root 2 comma pi over 4 is one such representation, and so is let's see, a root 2 comma negative 7 pi over 4, and so is a negative root 2 comma 5 pi over 4. So there's just an infinite number of representations for that point. So when you're converting from Cartesian coordinates, which is rectangular coordinates, to polar coordinates, you need to find a way to restrict that down to just a single answer rather than an infinite number of answers. So this is what I mentioned in the very first video when I said there's not a one-to-one relationship between rectangular coordinates and polar coordinates. It's one-to-many, actually. So here's the theorem on how to convert. A polar representation, and the word a there is important because there's an infinite number. So a polar representation of the rectangular coordinate x comma y is r comma theta, well, like we're used to, where r is equal to the square root of x squared plus y squared. Notice in this case, with this definition or this theorem, r is forced to be positive. Again, there's an infinite number of representations for that polar coordinate. However, we're going to choose the representation where we're forcing r to be positive. It just helps us out, that's all. And theta is a quadrant appropriate angle such that the tangent of theta is y over x. All right, let's kind of dive into this theorem a little bit to really boil down how to do this. And usually when you do a justification or a proof of a theorem in trigonometry, generally you stick to quadrant 1 just to keep the logic clean for those who are not used to trigonometry. However, in this case, we're going to go ahead and do this in quadrant, let's say 3. It doesn't really matter if I did 3, 2, or 4, or 1, but I think 3 is a little bit cleaner for the beginning of the argument. All right, so how would you convert from some point right here, let's just call this x comma y, to its polar coordinate? Well, the first thing to note is if that point is x, y, that means that you've gone along this axis, x units, and you've gone along the vertical axis, y units, to arrive at that point. X is going to be negative technically, and y is going to be negative, but you've gone x units to the left and y units down. And when you're figuring out what this point is in terms of polars, you want to know what is the distance from the origin to this point right here, and that would be the hypotenuse of this triangle. And that hypotenuse is actually, via the Pythagorean theorem, the square root of x squared plus y squared. And so there is the first part. R is the square root of x squared plus y squared. It's just right triangle trig. Actually, not even that. It's just the Pythagorean theorem. Next thing you need is to find what is this angle right here. That is theta. We want to know what that angle is. Well, instead of finding theta, we're going to find theta hat, the reference angle, theta hat. And the way we're going to do this, and I should have said this, oh no, we're fine. The way we're going to do this is we're going to go ahead and say the trig function that relates this reference angle to our x and y values is tangent. I hope you would agree with that. So we know that the tangent of that reference angle is y over x. This does not match the theorem. We want theta, not theta hat, and we want the tangent of theta to equal y over x. Well, finding the reference angle is incredibly important. And the reference angle is going to be the tangent inverse of, if you follow my video series, the absolute value of y over x. If you're not one of my students, or if you've never seen one of my videos, I'm just going to say it very quickly here. When you use an inverse trigonometric function to find an angle, you should always use the inverse trig function for the absolute value of that ratio right there, and consider the angle that you've gotten as the output of that operation to be the reference angle. So really, when you're using inverse trigonometric functions, you should only be searching for reference angles. And then you will use the SIGN sign, the plus or minus sign of your ratio, to determine what quadrant your reference angle is landing in, and then finish out the problem that way. So in this case, when we find a reference angle, we're just going to go ahead and take the tangent inverse of the absolute value of that ratio. That will return the reference angle. And then you can find theta based on the quadrant of the point x comma y. And that would give you everything. So that is the statement up above, and theta is a quadrant appropriate angle such that tangent of theta is y over x. So it's very important here to see these the examples in action, so you really understand why these choices are made. But I also want you to realize that this goes heavily in line with what I always say trigonometry is. Trigonometry is all about reference angles and quadrants. Over and over again. That's what, if you get anything from a trig course, you should get the fact that it's all about reference angles and quadrants. The entire course is pretty much about that. Yes, there are little other things that occur, but almost everything revolves around reference angles and quadrants. Now let's put this into action, because just seeing the theorem is not going to give you a good, strong understanding of how these problems work. So let's convert the Cartesian coordinate 3, 4 into a polar coordinate. You don't actually have to plot this, but I'm going to, because I need to know the quadrant. Obviously, we can easily see, because we've worked with Cartesians for so long, we know that's a quadrant 1 point. So that'll be somewhat useful. If you forget what the theorem is, well, you at least should know that you need this distance. That distance is r. And if you just know the Pythagorean theorem, then you know what r is. R is equal to the square root of x squared plus y squared, which is equal to the square root, in this case, of 3 squared plus 4 squared, and in this case, it'll be 5 altogether. So r for us is 5 units out. And again, when you use this conversion process, your r will always be positive when you're converting from polar or from Cartesians to polars. Now, to find that angle that we turned through to get to that point, you're going to say, well, the reference angle, not the angle, but the reference angle, is the tangent inverse of the y value, the positive y value, I should say, over the positive x value. Again, I should probably have written it that way. Tangent inverse of the absolute value of y over x, which is, in this case, the tangent inverse of 4 over 3. This is not going to be a special ratio, so you're going to have to grab a calculator. If you grab a calculator and you punch into that calculator tan inverse of 4/3, you will get an output of 53. I'll just round to the nearest tenth. So roughly 53.1. And I need to zoom in, otherwise my ink goes wacky. So roughly 53.1 degrees. If you want to answer in radians, you can answer in radians as well. But generally when you're doing ugly numbers like this, I kind of stick with degrees for some weird reason. But that's our reference angle. Now that we have the reference angle, we'll state what quadrant we're in. Our point is in quadrant 1. So we have a reference angle of 53 degrees in quadrant 1. That means that our actual angle is 53.1 degrees. Again, I should say roughly, right? 53.1 degrees. And therefore, this point, 3, 4, in polars, I should also say roughly, is roughly 5, 53.1 degrees. Remember, it's R first and then theta second. It's alphabetical order, R and T. All right, so that's a first conversion. And the reality is, because that's in quadrant 1, that's not an exciting conversion. So let's do something that doesn't land in quadrant 1. Here's a point, 1, -2. So I go over 1 down 2. So now we have a quadrant 4 angle. Whoops. 1, -2. And we want to convert that to polars. Well, the first thing I'm going to do is note, again, if you forget the formula, it's totally okay. You can recreate it just by saying, I need this distance. Well, I happen to know, so I need that distance is what I meant to say. I happen to know this leg length is 1, and this leg length technically is -2, but you can find the hypotenuse by using Pythagorean theorem. So R, in this case, is going to be the square root of x squared plus y squared. Well, in any case, it's x squared plus y squared. But in this case, it's going to be 1 plus 4, or root 5. So that's the radius of that hypotenuse. And now to find the angle. To find the angle, we'll go ahead and deal with theta hat. Theta hat, remember, is a tangent inverse of the absolute value of -2/1, the absolute value of the y value over the x value. Shoot, I should have written it that way. Y over x. And in this case, that would be the tangent inverse of 2. And that is approximately, because that's not a special ratio, so we have to resort to using a calculator. Tangent inverse of 2 is roughly 63.4 degrees. Again, be very cognizant that your professor might require your answers in radians. So just read the problems when you read the instructions for the problems when you're doing them. Make sure you're in the right angle measure. All right, that's our reference angle, but we're in quadrant 4. So we need to adjust that angle. If you have a reference angle of 63.4 degrees in quadrant 4, depending upon how the question is worded, if they don't tell you how to respond, but instead just say, convert this to polar coordinates, then they're not restricting you or your angles to be positive. So I would write this as roughly root 5, -63.4. In other words, I turned down into quadrant 4 by 63.4 degrees. If you're working in an online homework system and they say your angles must be between 0 and 360, well then take 360 and subtract off that 63.4 degrees. So I'll say, or it could have been written as root 5, 296.6 degrees. Just depends on how the question was asked. Either of these, in fact, there are an infinite number of representations, so either of these are fine. But that's how you do it. Very, very nice. Notice it's just about reference angles and quadrants for finding that theta hat. And using tangent inverse, you always use tangent inverse or inverse trig functions on the absolute value of the ratio. All right, another example. We'll go ahead and Let's quickly plot out -3, so back 3 units, down 2 units. So -3, -2 is right there. So we know we're in quadrant 3. Let's go ahead and start the conversion. I know r is going to be the square root of x squared plus y squared. That's going to be the square root of 9 plus 4, which is equal to root 13. And we also know that theta hat, or the reference angle, is the tangent inverse of the absolute value of y over x, which is the tangent inverse of, 2/3. And again, not a special ratio. Generally speaking, you're not going to get them with these types of problems. So tangent inverse of 2/3 is roughly 33.7 degrees. Again, if your problem requires you to work in radians, please do so. That's our reference angle, and we are in quadrant 3. So if I have an angle in quadrant 3 with a reference angle of, 33.7 degrees, that means I've rotated through 180 plus that 33.7 degrees, and that is 213.7 degrees. So theta is roughly 213.7 degrees. There you go. So now I know a polar representation for this point is going to be approximately square root of 13, comma, 213.7 degrees. There you go. So it starts to get easier as you move forward. It's not like a terrible amount of work. This final example actually is not like crazy different. In fact, let me do one thing here. I'm going to change that -6.5 to a positive. The only reason why is because, in fact, I think I have a way of doing this accurately. Let me use this. There we go. All right. So the only reason why I'm doing that is because we've already had examples in quadrants 3, 4, and 1. I'd like an example that's in quadrant 2. So let's go ahead and convert that example or that point to polars, and let's do this in radians. Why not? So it's not really any super difference between what we've been doing, but let's go ahead and do that. So in Cartesians, the point looks like this. Back -10.8, up 6 units. So something like this. I don't need to be super accurate. There we go. I know the radius, the distance there, is given from the Pythagorean theorem. So r is equal to the square root of that -10.8 squared plus 6.5 squared. That, I'm going to grab a calculator. So I'm going to leave it like that for now. Well, I might as well just grab a calculator and do it, right? So the square root of -10.8 or 10.8 squared plus 6.5 squared is going to be roughly 12.6. So roughly, my pen is doing wacky things today. Roughly 12.6. Very approximate, right? And then we know the reference angle is going to be the tangent inverse of the ratio of y to x and their absolute value. So 6.5 to 10.8. So I don't worry about negativity. I just worry about the y over x without negativity. And I just remember, I want this in radians, so I'm going to switch the mode on my calculator to radian mode. And I will go ahead and do the tan inverse of 6.5 over 10.8. And I get the following in radians, roughly. We'll round to 2 decimal places because radians kind of requires that level of precision. So 0.54 radians. That's my reference angle. Now I know I'm in quadrant 2. So if you're in quadrant 2 and this reference angle is a 0.54 roughly, well then the big angle here, theta, is going to be pi minus that. Theta is approximately pi minus the 0.54. So I'm going to go ahead and grab my calculator and just calculate pi minus that number, and I get approximately, again, rounded to 2 decimal places, 2.60. That's again in radians. So this point in radians, or in polars, sorry, is, let's see, blue ink, and what do we have? 12.6. So this is approximately 12.6, comma, 2.60. This brings up kind of an interesting little thing here. So this polar coordinate, as it's written, looks like it's a Cartesian coordinate because it doesn't have a degree sign on the angle. But unfortunately, that's just how it is when you're working in radians, that your points in polars kind of look like Cartesian points, right? So that's just something that you have to be aware of, that when you're forced to work with radians, that and if your radian angle does not have pi in it, then it's going to look like a Cartesian point. This is just how it is. Don't worry about that. All right, so this problem and this video is completely done. The next video, we're going to focus on converting equations. So now we're going to start working beyond just points and start working with equations that are given to us in polars and convert them to rectangular form.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way. Cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Just listen close. Don't talk too much that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry. Don't whine. Just